Hello friends, welcome back. Today in this video, we'll learn how to set up Maxwell design for your transformer. I'll walk you through the essentials, starting from creating excitations and winding, to configuring Eddy effects and establishing an analysis setup. In previous videos, we have created this 1:1 transformer model in PEMAG and performed some basic design analysis on it. Now it's time to take things a step further. In this video, we'll create and configure a Maxwell design. This will set the stage for deeper analysis in our upcoming knowledge pack tutorial. So let's not waste any time and dive right into it. So the first step in this process is to create a Maxwell design from this model. So we'll select this option FEA Eddy current and we'll click on the 3D design type and we'll keep this option enabled, that is apply symmetries. So what this option does is it will create either a half symmetry or quarter symmetric model based on the symmetries present in your design. So this will help us to speed up our simulation. So I'm keeping this as a enabled apply symmetries option. Now we'll select what test we want to perform. So for now it is not much relevant. So I'll just select a short circuit and hit on OK. It is saying overwrite the existing project because I have already created one project. So it is asking me whether you want to overwrite or open the existing project. I'll select overwrite the existing project because we want to create a new project from scratch. I'll hit the OK. Now you can see it's opening electronic desktop. It might take some time to create a project. Now you can see on window it has opened Ansys electronic desktop. It started building a model. I'll just zoom out a bit so you can see the project creation. Now you can see it is creating the bindings. Now primary is completed and it is creating a secondary one. It will take some time to complete this. So we'll just wait for a while. Yeah, it has completed the project creation. Now on left hand side you can see all the elements involved in our design. I'll just collapse everything. So you can see this is secondary winding, this is primary winding, core and everything. For now I'll just hide these boxes so I can edit the design further. So we'll start with the assigning the excitations. Now on the left hand side you can see under the excitation tab already some excitations are there. Maybe it is not visible properly on the window. So what I will do, I'll also hide these windings. Here from this tool menu you can hide the selected portions. I'll also hide the code. Now you can clearly see how it has assigned the excitation by default, but for now I'm just going to delete everything. So before that I'll just select this tools, record script file, and you know I'm a big fan of recording the script. I'll just name it as a basic config and I'm going to save it in desired location here, basic config, save. So the scripting, this is very powerful tool, the record script. So what you are doing in this GUI, it will record it as a script in Python script in a background, and that script you can use it further in your simulation, in your design design configurations. So this will help you a lot to speed up your initial setups. So this part I have covered in my previous videos. You can go and check it out. Right now I won't take it. I won't go deep into it. I'll just record it, so we might use it in our future videos. So now I'm going to delete these things, all the current excitations, everything is deleted, and now let's just start with the assigning coil terminals to primary winding. So go right, select, and then right click, then go to assign excitation to coil terminal, and I will name it as IPP. IP for primary and P for positive terminals, and I'll just swap the directions. So okay, and on the left hand side you can see it has created the coil terminals. Same will do for this section. Assign excitation coil terminals, then I will name it as IP underscore N, and direction I will keep this, because if you see this, so you can see current will enter in this terminal, it will flow to the winding, and it will go out like this. So that's how we are configuring and telling it to Ansys, this is the way we want it. Now same for the secondary. We'll go assign excitation coil terminal, name it as IS underscore P. I will swap the direction. Okay, and now for secondary negative terminals, RS underscore N, swap direction will keep as it is. Now you can see on the left hand side all the terminals are created. Okay, so now we will create a winding. So winding just help us to organize all this terminal into a section. Let's say if I name it one, I create a winding one as a primary, I will assign all the terminals, coil terminals, which belongs to primary under this winding tab. Oh, sorry. So I'll name it as primary. And then if I have to create some excitation, then it's I have to create some user defined excitations. So it's very easy to change the current through all the coils simultaneously. It just make our life easier, and also we can find out the inductances between these primary and secondary windings. We can find out the self inductances, leakage inductances. So the creating a winding just help us with that. I'll assign 1 ampere. Okay, I'm selecting solid. If you are using XY, you can go ahead and standard. Okay, same way I'll create. Same way I'll create my secondary winding. Type is current. Excitation we are giving current excitation. I'll give -1 ampere current. So because I want to perform a short circuit analysis, so that's why I'm giving a -1 ampere. Okay. Now next part is we have to assign this coil terminals to this winding. So we have to add these terminals in the winding. Now I will just add all the primary terminals. You can see here. So I'm selecting all these primary terminals. Just hit OK. Now you can see all primary terminals under this winding, primary winding. Same will do with secondary. And now for simplicity, you can select this option, terminal not assigned to any windings, and it will just show you the secondary winding terminals. So let's select all the secondary terminals. Okay. Now you can see all the primary terminal are assigned under the primary winding, and secondary terminals are assigned under secondary. Yeah. So next step is to create a matrix, and will include primary and secondary. So what it will do is it will create an inductance matrix, of 2 cross 2 inductance matrix, which will give you the inductance and the resistance matrix. So basically impedance matrix it will create. Also a coupling matrix, how much is the coupling between these two windings, the magnetic coupling, that it will show, that it will create after we perform a design analysis. So for that matter, we are creating this matrix. So let's just hit OK. Now the next step is we'll just delete this our by default the setup which has been there by default, and I will add a new solution setup. Let's name it as setup 1, and I'm giving 25 kilohertz, which is my design frequency. And we'll keep other things to the default values, and let's just hit OK, and that's it. One more thing is we have to set up the eddy effects inside the windings. So we know when we excite windings and conductors with some frequency which has the current going to the windings having some frequency, then there the proximity and the skin effect will come into picture. So we have to turn these eddy effects. You can see for all the conductors that eddy effects are on. So we'll just hit OK, and now we'll perform the validation check for it. Now you can see it's giving some warnings. So this is because you can see our excitations and the symmetry, because this is a half symmetric model, right? So this is our boundary, which is a symmetry boundary. So our excitations are on that boundary. It might create some trouble, so better to shift this excitation a bit. So what I will do is I'll just select everything and go to the move tab, and this I will select the point of reference, and slightly on the left hand window you can see how much we are shifting it. So just by 0.5 mm I am shifting this coil terminals inside. So this won't change anything in our design, it just we are changing our moving our excitations bit inside. So this warnings won't come, but you can see our conductors are on at their place, but here you can see now this extra thing has appeared. So this is basically we have shifted our coil terminal bit inside, so that won't change any physics of this design particularly, so no need to worry about that. I just clear these old messages and I will again run the validation check. Now you can see there is no such issue in the design. So everything is ready now, and now we can go ahead and start analyzing our design. So what you have to do, you have to go on the setup which you have created, hit right click and then analyze. And here on the progress tab you can see it will start analyzing our design. So we have to just wait for it for some time. You can monitor the conversions under this section. Go right click on setup and go to the conversions. Now here you can see we see the plot. With every pass it is increasing the tetrahedron. Basically what it is doing is uh, it has created some tetrahedron. This is a FEA, right? So your 3D section has divided into some tetrahedrons, and it is calculating the fields inside that tetrahedrons, different parameters inside that tetrahedron. And with each pass, it is monitoring what is the total energy error, which you can see initially it is higher than 10%, it's around 20%, and then a delta energy, which will you can see from the next second pass. It's basically the energy before. It is the difference in a difference between energy in this particular pass and the energy in previous pass. So this is in the percentage term. So it was around 4%, and we have kept the target for both energy error and delta energy error as a 1%, which you can configure basically. If you go to the setup 1, here you can see the percent error we kept 1. So if you vary this, that target will vary. And let's say if you are in the initial phase of your design and you want to get things quickly, so you can initially keep this percentage error a bit high, maybe 5%, 10%, and you can quickly get the simulation result and you can make the design changes. And as you go further, your design is improved, you can keep this percentage error lower and lower. To you can make it more tight, so your design will be more accurate. Now you can see simulation is completed. We'll see the message tab. Yeah, normal completion of simulation on server. Now we can we'll go to the result tab. We'll click the right, we'll hit the right click, and we'll go to solution data. Yeah, now here you can see the inductance matrix or impedance matrix. So we'll select this RL, resistance unit and keep unit in 4, and inductance unit in millihenry. Now here you can see the primary to primary inductance. The first part is the resistance and second is the inductance. So primary to primary inductance is 0.32507 millihenry. Primary to secondary you can see, then secondary to secondary. So again, yeah, here you can see the coupling coefficient. This is the coupling coefficient between the primary and secondary. This will determine how much magnetic field will leak between primary and secondary, and ultimately it will determine your leakage inductance. So using this inductance matrix and coupling coefficient matrix, you can find out your leakage inductance, magnetizing inductance, mutual inductances. Now we will see how to visualize the magnetic field. So we'll plot a magnetic field on the plane of symmetry. So we'll go to the plane, we'll go to the sheets. So this particular sheet, on this particular sheet, we'll plot our magnetic field. So you have selected this plane, uh, then go to the field section, then B magnitude of B. So hit done. Yeah, now you can see how your magnetic field looks like. I'll just this was hidden. I'll bring it into active view so you can see it more clearly. I'll turn my view to the front view. Um, yeah, now you can see the field. So this is just a leakage field because we have given a excitation in that way, and you can see the field is more concentrated between primary and secondary. Uh, if you have given just excitation to primary, then you'll see the magnetizing flux. As of now, the net magnetizing flux is 0, so there is just a leakage field. In the same way, if you select the bounding box and go to the again same fields and go to the H field. So now you can see H field. So most of the H field is in between these two windings, and this gives us to rise of the leakage inductance. And if you want to see the field inside the core, now because this we have plotted on a 2D plane, same you can do. You can select the core, and in this geometry you go again, select Mag B, done. Now you can see the 3D distribution of it. Now for the starting, this is just okay. We got our leakage inductances, magnetizing inductances. With that sufficient target error to go into more detailed or more accurate solution, we can make that criteria more stringent. So for now, this is just okay. And that's it for today, guys. I hope you learned something new from this video. If you have any questions, drop them in comments below. Don't forget to hit that subscribe button. Thank you for joining in and see you soon in the next video. Stay tuned.